So far, we have been looking at the summation of arithmetic series, where we have a common difference of a number that we are adding to each term as we go through the sequence. But this time, we'll be looking at a geometric series, and in a geometric series, instead of adding a number to each previous term, we are multiplying a number. So for example, let's say we start with 1, and then we add 2, and since we're multiplying in a geometric series, we're going to continue with 4 plus 8 plus 16. So this is a geometric series. We started with a first term of 1, and we continued by multiplying a common ratio of 2 to each term. So this is how the summation of a geometric series looks like. So, how can we write this in a more general notation? Well, we commonly like to refer to the first term as a, so we'll multiply that by 1 in this case, and then we'll add a times r, because we have multiplied the common ratio of the previous term. So we usually denote the common ratio as r, and then we multiply it again, which is a times r, because we multiply it to the previous term, so that's a times r squared. And let's just go with this, so a times r cubed plus, and there are 5 terms, so a times r to the 4th. And one of the key things I want to point out here is that, again, we end at n minus 1 instead of n, because the first AR is 0, so it goes 0, 1, 2, 3, 4, even though there are 5 terms. So that's just something to keep in mind when we're trying to derive this formula. So what can we do with this sequence? Since we have a as the first term, we can actually just factor out an a from all of these, a times r plus a times r squared plus a times r cubed. So we can actually just factor this out. So we'll keep an a out here, and then we can go back to the 1 plus r squared plus r cubed plus r to the 4th. And this makes it a little simpler to think about, because we don't have to be confused by all of these a's in the middle. So we're just gonna have 1 plus r squared plus r cubed plus r to the 4th, which is interesting because that means that all we have to do to change a geometric series back into a first term of 1 is just divide by the first term. So now that we have that out of the way, we can start thinking about how to derive a formula based off of this. So this is a little more difficult because there's not a really easy way that we can see to simplify this expression. We can't just factor out something from all of these. We can factor out an r from these 4, but then we'll have to do that all the way until the end of the sequence. So it's going to take a much longer time. So one of the ways we can think about it is by thinking about just this yellow part, but we're going to think about it in a different way. So we'll start with less terms in the sequence. So we'll have 1 plus r squared. There's just 3 terms in the sequence, but it still has a common ratio of r. So in this sequence we have over here, what is a different way that we can express it? So one of the ways we want to figure out how to do this is by, first of all, we're going to define this as something, this entire thing. So we'll name that a. This 1 plus r squared. So now that we have that, it's easier to work with various different operations we want to do on this. so that we don't have to keep on writing this same thing over and over again in the future. So how can we reduce the amount of terms? Well, we can't just do the same thing we did in previous videos, as it's not that easy to simply add all the terms in reverse. It doesn't quite work that way because, as we can see from this example, if we put 16 plus 1, we get 17. But then 8 plus 2, 10, it already changes. It's not going to be the same. So a different way to think about it is, how do you want to cancel all of these r and r squared? And if we had a longer sequence, how do we want to cancel all of those terms that would appear? So one way is by using subtraction. But if we just subtract a from itself, we get 0, and that's not really helpful. So how about we just subtract the r and r squared? So how can we do that as a modification to a? Well, if you notice, a times r is actually just equal to, and I'll write it slightly shifted so that it becomes clear what we're about to do. So a times r would simply just be r times each one of these. So we'll start with r times 1, which is r. I'll write it under here so that it becomes clear that there's going to be some cancellation possibilities. So we have r times this r now, so that's r squared. And we have r times this r squared, which would be r cubed. So again, we just multiplied this entire a by r. So a times r is equal to r plus r squared plus r cubed. So now it seems like we can cancel these out in the center here. It's just waiting to happen. So we're going to subtract a minus a times r. So a minus a times r, and this will be equal to, well, this and this will cancel out, this and this will cancel out, so we will be left with 1, and then since the negative distributes, remember we put a negative around this entire thing to subtract it, we'll have 1 minus r cubed. So 1 minus r cubed. So all we did was subtract a, and we subtracted a times r from a. So we were left with 1 minus r cubed. But we can't just leave it like this. We have to make sure that we go back to the original a. And we don't want to do things with this just yet. So we want to write this. We want to figure out how to go backwards, back to a, without literally unsubtracting. So how can we do that? Well, we notice that in a minus a times r, we have an a in both of those. So we can write a minus a times r as just a times 1 minus r, because notice that the a distributes to both the 1 and the r. And as we have seen, this is just equal to 1 minus r cubed through our definition over here. So to go back to a, all we actually need to do is divide by 1 minus r on both sides, which will give you 1 minus r cubed. And I'm assuming here that the common ratio is not 1, because if we have 1 minus 1 is equal to 0, we can't divide by 0. But if you think about what happens when the common ratio is 1, well, we just have 1 plus 1 plus 1 plus 1. So for all common ratios other than 1, this formula, this division operation should work properly. So now we have a is equal to 1 minus r cubed over 1 minus r, which is very useful now because we didn't actually have to use these middle terms as we saw in the top. Now, to see the actual uses of this, we want to generalize this to an n number of terms, as always, just to see how this will turn out. So let's define b, and in this sequence we'll have a first term of a multiplied by all of the terms in the middle, which will go from 1 plus r squared, and this will go on until r to the n minus 2 plus r to the n minus 1. So the reason why it goes all the way to n minus 1 instead of directly to n is because, as you'll see here, when there are 5 terms, this the r to the power of starts counting from 0. So we have 0, 1, 2, 3, 4. So in this 5-term sequence, we have r to the 4. So that's a good way to intuitively realize that we have an n minus 1 here. So now what can we do with this? Well, similarly to the previous way that we did with this a sequence over here, we'll simply multiply everything times r. So here we have b multiplied by r, and in this way we'll be able to show that when we subtract this, and it's also easier just to kind of not think about that a anymore, because what we'll do eventually is actually just multiply it back together and it'll distribute to everything regardless. So just think of that as being on the outside of the equation, and so far we'll just be doing operations on this 1 plus r squared and so on. So now we want to multiply r to this entire thing, so I'll keep this over here, and we want to multiply r. So now we'll have r times 1, so we'll have r, and I'll write this over here, and then we have r times r, which is r squared, and instead of going to n minus 1 this time, we have r to the power of n minus 1 instead of n minus 2, and r to the power of n instead of n minus 1. And now I know this is a little weird because these two match up but these don't, but that's only because I wrote the first 3 terms of this and the last 2 terms of this, so it's a little deceiving. But over here, the key point is to realize that the middle ones, all of these will cancel out and we'll be left with, well, that's what we'll look at. So when we subtract it like before, we have b minus b, and then of course we're multiplying this r to the b, and this will be equal to, the a is still on the outside of everything, and we notice that all of these will cancel out. All of these cancel out with these. This n minus 1 will cancel out to this n minus 1. This r to the power of n minus 2 will cancel out with what's over here, another r to the power of n minus 2. And we are left with 1 minus r to the power of n, because remember we subtracted all of this, so this minus distributes to everything. So 1 minus r to the power of n, and now we notice that this can just be written as b minus b times r, can just be written as b times 1 minus r, and this is equal to, as we saw over here, this is equal to a times 1 minus r to the n. And this is the very nice thing over here. We finally have b, if we divide by 1 minus r on both sides, assuming that the common ratio is not 1, we have b is equal to a times 1 minus r to the power of n over 1 minus r. And this is a really nice formula over here, because it's very, very cool how just shifting the perspective and multiplying by r to cancel out all these middle terms leads to this amazing realization, 1 minus r to the power of n. And this is very impressive, just like how impressive it was for the arithmetic sequence. See, and now we can try testing things out with this. Let's just try the sequence over here. So we have 1 as the first term, so a will become 1. And then we have r to the power of n. So what this means is the common ratio to the power of the number of terms. So I'll just write this over here just to finalize what I have to say. So this is 1, remember, 1 times. I'll just also write it over here. I know it's not b anymore because we're substituting numbers, but 1 minus, and then r to the power of n is 2 to the power of number of terms in the sequence, which is 5. So 2 to the power of 5 is also 32. 1 minus 32 over 1 minus r, which is 1 minus 2, which is negative 1. And so, if we complete this, this becomes negative 31 over negative 1, and we are left with 31. So we have 3 plus 4, which is 7, plus 8, which is 15, plus 16, which is equal to 31. And we have verified our formula with this sequence over here, and we can be confident. We can be confident that we have done the right steps over here. So I hope you found that interesting. These sequences are very interesting to some, and it's very nice to see how creatively they can be canceled to turn into these simple formulas, relatively simple formulas that we have over here. So I hope you liked the derivation, and we'll continue later with some example problems where we use these formulas.